Okay, welcome to the afternoon session. First up, we have Thomas Szymanski, who is going to be talking about the future of power grids.
Yeah, thank you for the introduction and welcome back after lunch. As already mentioned, I'm Thomas Szymanski and also working at Digico, and I'm presenting you today the topic of navigating tomorrow's power grid challenges, heuristic synthesis of optimized feed areas with GeoPandas. And the topics will be structured as follows. First, a few words about Digico, my employer, what are we actually doing and who are we? The second one is the actual problem statement. So why grid areas? Why do we care about this topic? Third is the fun part, all about the modeling. Which input data did we use? Which restrictions do we have? And how did we all turn this into a custom developed algorithm to solve our problem? I've also brought you, let me just quickly close this, sorry. In the fourth part, I've brought you some maps and animations with the results to showcase the algorithm in action. And the last point is the enhancement and outlook. So what are we currently working on and what are the limitations? So Digico, the title is Forecasting Climate Change because this is what we do on a local level. We are trying to mitigate, let's say, the problems of the green transition and the climate change on a local basis in the municipalities. And I've brought a few products that we currently have. As a software company, we are very data-driven. And so we have a digital twin that is combining statistical data, building data, consumption data, and infrastructure data all into one product where the municipalities and also energy companies can have their information ready in one product. The second one was already mentioned in two talks before. We are a lot about heat in Digico and the heat transition. And we are currently building a software product around the heat concept, which is showing the municipalities where to act and where they can change to green heating technologies. The third one is the INGA product. This is all about intelligent charging infrastructure. So that's it for Digico for now. Let's dive into the problem. What are we actually talking about with grid areas? I've brought you a little picture showcasing the development of household-related flexible consumption devices. So what is part of these devices? For example, electric vehicles and also heat pumps. And we see on the left side the number of heat pumps and electric vehicles in 2022 and the development until 2035. And I think we can see that we will have a huge increase, at least a forecasted increase in the numbers of electric vehicles that we have. So, for example, from electric vehicles 2022 with 1.4 million, we are going to increase to about 30 million in 2035. So this is just 10 years from now and really a major development that will take place. The same applies for heat pumps as we are increasing from 2 million to around 10 million in 2035. It's not as significant as with the EVs, but still, an interesting development that we see. And on the right side, you can see that this directly translates into the power consumption that we see. And this power consumption is all taking place at the building level. And so is also straining the grid at the building level. For example, for the EV charging, we can see that we go up from around 20 gigawatt to like almost 350, which is a very huge increase. And the problem with this building-related power usage is that the German grid infrastructure is unfortunately not ready to produce so much power and to supply it to the households. So How does our German grid infrastructure currently work, and how do grid areas really come into play here? I've brought you a small picture of the, or simplified picture of the energy networks that we have, which can be roughly divided into maximum voltage, high voltage, and medium and low voltage that we can see here. And what we are taking, or what we are referring to right now with grid areas is the area that is covered by one electrical transformer, because once the produced power is transformed from the medium voltage zone into the low voltage zone, there are these electric transformers in between that convert it to low voltage. And so grid areas are, in our sense, the buildings covered by one electrical transformer station. And this is likely a geometrical problem as well, because you have a polygon that is forming around these buildings that will be supplied by this electric transformer station. And so what do we want to do? We want to create these grid stations grid areas from scratch with a custom built algorithm. And why do we want to do this? First, we can have a very good status quo analysis based on this, because you can see, okay, if we have an algorithm that is saying us, okay, where do we need to put electric transformers and how many, then we can see, okay, where do we have current bottleneck in our supply chain, and where would we need more transformers also already at the status quo. Based on this, we can go even further and take into account future scenarios like the ones I presented, but there can be a lot of potential for analysis in this space, because we can see, okay, which people live where, which people are likely, for example, to buy a heat pump in the future, and so on. And if we put this together with the current status quo, this has a lot of potential to identify and prioritize the regions in a municipality where the infrastructure is most likely to be at risk, and where we have not enough power in the sense of electric transformers to support the demand. And so this is our goal, that we support stable grid network, and that we help the municipalities in planning and investing at the right time and in the right place, let's say. So let's start with the modeling. The first is the input data, of course. So what do we know? Digico has a lot of data that we can use, but one critical source is the building data. I've provided you some sample data just to showcase this. We have the building shapes of buildings in a municipality, and we also have a basic estimation of the power demand on a building level. And what we sometimes know, it always depends on the region or on the project that we are working on, is do we know the position of electric transformers? This can be either yes or no. It's roughly 50-50 that we know it. But also what we mostly don't know is if we know the positions of these transformers, how are the actual cables running to the buildings, so the real grid path to the buildings. This is sometimes we mostly don't know. And what we try to do first now is to create an algorithm that is starting from this baseline of what we actually know, so the buildings and the power demand, and is creating a grid area from that data. But of course, restrictions apply, and as we are mostly focusing on transformer stations, you would have guessed that we have the restrictions related to these stations, because they are not able to handle any kind of power load, let's say. So we have defined minimum, ideal, and maximum values. For example, for the power that it can, or the power load that it can supply, we've measured this in megawatt hours, and it goes from roughly 100 to 1,300. So it's a big range, and in between we have with 500 the optimal value. The same applies for the number of connected buildings. We have a maximum threshold of 140 there, and also for the area covered, because you have to, you can't just create indefinitely big areas there and all connect them to one transformer station. And these are the restrictions that we kind of used to construct this algorithm. And now I've provided some little code example or pseudocode, let's say, to showcase what it really does, because it's simple in the end. So at the beginning, we are going to calculate the optimal normalized restriction score. So for each of these restrictions that you have seen before, we are calculating an optimal normalized value by taking the optimal value divided by maximum minus minimum. So they are all in the same range, basically, from a numeric perspective. And after this, we reduce down the building shapes that we saw, which are polygons and multi-polygons, to a representative point, which is like just the center point that is on the surface of the building itself. So this is like giving us the municipality and its buildings just like, with point geometries. And we define the most center building in this municipality also via GeoPandas. And after this, the algorithm currently starts to add buildings to a grid area that we now define. So how do we do it? So we start a loop and say, okay, our overall score must improve with each iteration. So if it doesn't improve from the iteration before, then we stop. And also, of course, we can't exceed the maximum values that we defined for each of the restrictions. And if no buildings in the whole municipality are left, then of course we also stop. And so we just say, okay, we have the center building that we defined, and now we are going to add the nearest buildings to this grid area. And you add the next building, we update all the restrictions and the scores. So we calculate the current score that we have by taking the current value per restriction divided by max versus min. So let's say you have like 5 buildings included, then the score is like really low. And we also calculate the overall score by summing up all the restriction subscores. And this is the basis for the next iteration loop, because we then compare, did we have an increase in the real result value or in the score, or didn't we have it? And so it's basically a pretty simple implementation. Let's take a look at the results, because I've tried to create a little animation here to showcase this. And as you see, we are starting in the bottom right corner, and we are basically like circling outward and integrating more and more buildings. On the right side, you can see the restrictions or the scores per restriction. And as you see, we have the optimal values and the maximum values. So for energy, for example, it's around 40%, the optimal value. And now we are increasing with the current value for buildings. We exceed the optimal value. And at that point, it's now it's already finished the animation, but that's no problem, I think. So we can see that we basically circled outwards from the beginning building, greedily integrated new buildings into our grid area that we created. And what we did was we tried to optimize the restrictions or the scores as a whole. So in this example, we have a more rural structure, urban structure, sorry. And thus we are very low on the area value of the restrictions. But we over exceeded buildings a little bit, and energy is about the optimal values. So yeah, as we didn't cover as many area as we could have, we had the potential to go a bit higher on the building score. Yeah, so this is this is our way to like have a good balance of the restrictions in the end, so that we don't get too close to the maximum values, but also try to stay close to the optimal values in the end. Yeah, this buildings would now form a grid area, so we could form a polygon around this and say, okay, we have to put an electric transformer station here and connect all the buildings to it, and we would have like the first step ready. But of course, there are a lot more buildings in that municipality. So in the next step, we are doing the same thing again, but for the whole municipality. And yeah, this is going to cover all the buildings in the municipality at the end. Some, as you can see, are way, way bigger, that are more in the rural parts. And yeah, the one I showed in the center is like a really small one. Yeah, and so we basically fill out all the holes now. As you might have seen, in some iteration steps, it seems like we are creating two grid areas at once. This is not a problem with the animation, but it's more a thing with the algorithm, which I will come to now, because we did further work on this, and there are also some limitations I'd like to explain. Yeah, sometimes it can happen that this grid area is expanded. So you integrate the next building, and there is another grid area in between. You jump over that and go to the next building that is far, far away, but not already in an existing grid area. So you have these little islands that you create, and what we did is that we provided a post-processing algorithm to basically take all these islands, identify them, and then look at the neighboring grid areas. So you look at the scores, and you just say, okay, if I would add this to the neighbor, would it hurt the scores, or is it a good solution to just add it to an existing one? Yeah, this is a thing that we already did. Another one is non-synthetic algorithm. As I mentioned in the input data section, we have sometimes also knowledge of where the transformer stations actually are. So this doesn't mean that this is useless, but it's further, it's more like refining the algorithm a little bit. And we've adapted it so that it just starts outward from the existing transformer stations and integrates the buildings. And this is also a very, very good use case to do some real world analysis on it. So if you have the data, we can also like integrate existing transformer stations, or also like existing building connections into all of these analyses that we do on top. Yeah, this brings me to the next point. So further analysis, what are we actually doing with this right now? For example, we are trying to determine the sensitivity of the grid areas that we have, either synthetic or like on a real world basis. And we take these trends that we see with the electric cars and try to project them onto the grid areas that we defined there. And this leads us to a very good estimation of what is going to happen in the future, and are there enough electric transformers or not, for example. The same applies to the heat transition trend that I showed at the beginning. This one is also very interesting because it really much relates to what kind of people live in a building. So, for example, a really detached building in a really good neighborhood is much more likely to install a heat pump than a building that is not. And so we are trying to put more data into the analysis of the scenarios that will come to happen. And say, okay, where do we need to invest in the infrastructure that we currently have, because yeah, it is very likely that it may not be enough. And yeah, another topic is the ideal placement. So if your result is, okay, we will need in a region 2 more electric transformers, then another interesting topic is where to place these additional transformers that we need. But yeah, we are currently working on this as well. So I think there are a lot of yeah, interesting analysis left to do, and more to come, I hope. Yeah, so thank you for your attention. And do you have any questions?
Yeah, thanks very much. Does anybody have any questions?
Hello. Yeah, thank you so much for that great talk. I think when one of the slides you mentioned that the goal was to create low voltage grid areas. I was just wondering what would be the transitional cost for the revamp. Let's say if we pick up this new plan, how much would that cost for the municipalities to implement that? And a follow-up question is, did you also kind of forecast until when would the new plan with the new set of transformers be sustainable to keep up with the growth of the energy consumption in the future? Like when would the next revamp be required based on the current consumption trend?
Yeah, I think that's a very good question. First, let's say that when I showed you this example of the synthetic grid areas, most likely when you go to work with a municipality or you have a project with them, they mostly supply you with the locations of existing transformer stations. So this is more about analyzing where it may not be enough and where to put new ones. So it's not about taking the existing layout of the grid infrastructure and change everything, but more about what to do in the future and where to add something. And so, yeah, this would be also a very interesting analysis, because you could define different electric transformers with different power supply that they can handle, and analyze also the cost that is created by adding them. And if I understand your second question correctly, this is about the time frame that we want to have a better insight into when the power supply will need to be generated, or?
By when potentially would we need another set of addition of new set of transformers in the future? Like until when would the new additions be sustainable? If that makes sense.
Yes, yeah, I think this really much relates to the average kind of power load that the electric transformer can handle. And for example, I can show you something from a real world scenario. So this basically is the analysis what would happen if we would right now have 30 million EV electric vehicles. And what you see there is the colors are measured based onto the load that the transformer can handle in percent. And the areas that are colored dark red, they are above 140% of the current max. So you would at least need 2 additional transformers there to supply the energy. And for example, let's say the yellow area, it's just 20 to 94%. This is something where you would say, okay, we don't have to do something now. We could watch it closely, but there is no, you don't need to act immediately. But and then it's a thing. Then it's basically, I think, about formulating or well-formulated scenarios about the future, where you say, okay, for the year 2030, we have the following expectation, and to map this into our model, I'd guess. So it's would be perfectly doable to have the an animation about the development over time. Yeah.
All right, we have another question down the back and still a couple of minutes if anyone
Thank you
wants
for
to
your
ask one
talk.
after.
Yeah, so in your talk, right, so you only use like OpenStreetMap data, which is quite limited, and you mentioned you can also integrate more layers of data to make the result much better, right? So I'm really curious, if you want to get some data, then where do you typically to source it from? For example, in your current slide, so you got some like extra data for EV traffic or stuff. Yeah, so where do you typically get? So from your customer, or you have to contact to local government or maybe some departments for the data?
Yeah, that's also a very good question, because it's always very challenging. We use OpenStreetMap as well, but we are having a lot of data sources. For example, we are buying data from a data provider that is also having not just the building shapes that we see here, but also a lot of attributes. We try to gather socioeconomic data from free sources. We also get what you already mentioned. We get a lot of data once we are in an actual project. So if a municipality wants to plan, like, okay, what's going to happen until 2050, then they try to provide us with the data that they have. So this relates to consumption data, for example. So for some municipalities, we have the opportunity to get those real consumption data and can plan based on that. And I think we also got data that's based on this car movement and traffic data and stuff. But yeah, it's always challenging. If you have a lot of data sources, it's always challenging to combine them and to get them in the quality that you need. So it's not just adding a lot of data sources, but if you want to really use them, you have to make sure they have the same format and align well. And
Okay, thank you.
Okay, we still have another minute or two if anyone wants to ask another question. No, looks like you're off the hook then.
Yeah.
Oh, wait.
Thank you.
One more.
I was wondering, I think this question sort of came up this morning as well, in terms of like planning the future. At least with us, where space is very limited, a lot of planning is going on and densifying the areas with increasing the height, the altitude of buildings, etc. So to bring more people into the same space, which would also lead to more energy consumption, right? And I have no idea what's the life cycle of such an infrastructure, but is there any emphasis on synchronizing these kind of like developments, so to speak, both socially but also technically? I would also assume that the technical infrastructure would become more and more efficient, or the batteries will shrink, etc., and whatever. No idea. Or are those processes totally individual and parallel at the moment?
I think from my perspective, or from my experience, like problems with that you described with the building height and densifying the population, I don't think that we really factor this in at the moment. But from my perspective, it's like a data problem. If you would have data that could describe this, it would be possible to get it into the model, let's say. But for now, we don't really take this into account, honestly, because we try to focus on those trends that have the most impact, let's say.
Okay.